good evening to Dr. Izami, our internal examiner, and Dr. Nick, our external examiner. Hope everyone is doing fine. Today, me and my fellow groupmates will be presenting about our topic, conversion of plastic polypropylene to syngas via gasification process for production of methanol. So, for our presentation outline, my name is Sanjeev, and I will be presenting on the introduction, problem statement, objectives, and the conceptual design of the project. My groupmate EZZA will discuss about the literature review and the conceptual design of the project. Economic evaluation, instrumentation, and control strategies will be discussed by YUAN, whereas Farah will present about the preliminary hazard analysis and heat integration. Lastly, KUOL will present about the safety and loss prevention, as well as the conclusion of the project. So, for the introduction, as we all know, plastics are often used in daily applications because of its interesting properties such as liquid weight, mechanical strength, corrosion resistant, and many more. The rapid increase in plastic usage has led to a significant amount of waste accumulated in the landfills. Plastic waste are considered to be a non-biodegradable as it takes thousands of years to decompose. Besides that, depletion of fossil fuels has urged us to seek for alternative source of fuel. Waste plastics can be recycled in many forms and be put into good use. Our problem statement would be that with the drastic increase of waste PP due to the wide applications of plastic product, plastic waste have occupied a major space in the landfills. Furthermore, the plastic waste are non-biodegradable waste, hence urging us to find a solution on how to manage this amount of plastic waste. Feed waste polypropylene can be a potential feedstock for methanol production as it can be obtained for a good price, as it is a waste product. PP can be converted into methanol by steam gasification to produce syngas, later converting the syngas into methanol by partial oxidation. The main goal of the project is to conduct the feasibility analysis and to research the potential of methanol plant with PP as feedstock. So the objectives are, the aim of the project was to design a plant that can convert waste PP into methanol. The first objective was to design a chemical plant that is feasible for the conversion of PP to methanol. The second objective is to choose the most suitable location for the plant in Malaysia. Next is to design a conceptual flow diagram to obtain methanol. Besides that is to design a project that is safe to the environment by conducting hazard analysis. And lastly is to conduct the economic analysis of the project. Now I will pass the presentation to EZZA to continue with the literature review.
Sanjeev, I'm SYAFIRA. Now I will be presenting on the literature review. In the literature review, there are two parts, which is the first one is microanalysis and the second one is plant location. So from polypropylene, we choose to have four main products, which are methanol, syngas, dimethyl ether, and also hydrogen. For the first one is methanol. Worldwide, there are about 19 methanol plants with total of 110 million metric tons of production capacity. And in the Asia Pacific only, it is the top global, especially in methanol industry. Thus, for the Asia Pacific, the compound annual growth rate is expected to increase by 6.16% from 2018 to 2016. Moving on to our second product, which is syngas or synthetic gas. It is being widely used, especially in fertilizer production and also petrochemical industry. Thus, it is expected to increase from 22,505 megawatt thermal in 2019 to 501,932 megawatt thermal in 2024, where the compound annual growth rate is expected to increase by 12.6% in 2019 to 2024. For the third product is dimethyl ether. It is widely used and popular in power generation and also as a chemical feedstock in any production. However, even though the popularity of DME is higher, the supply of the DME is lower than the demand. Thus, it is expected to grow only about 0.1% from 2017 to 2023. And lastly, our product is hydrogen, where it is not only commonly being used in refinery but also in other industries such as semiconductor industry and also fertilizer industry, where for semiconductor industry, the compound annual growth rate is expected to increase by 5.5% in 2019 to 2025 and 1.54% for fertilizer industry from 2015 to 2020, where the total compound annual growth rate for hydrogen is expected to increase by 5.48% from 2019 to 2025. Moving on to our second part, which is plant location. We've been suggesting for about 3 plant location, which is the first one is Nibong Tebal Pulau Pinang, Port Klang Selangor, and lastly Sungai Petani Kedah. From here, in order to select the best plant location, we be done the weightage analysis where 12 criteria have been looking out, where the raw materials availability and market is our main key point in this criteria rating. Thus, from the weightage analysis, Nibong Tebal had the highest weightage, which is 124 compared to Port Klang 90 and Sungai Petani Kedah around 86. That's all for literature review part.
Thank you so
Thank
much,
you.
EZZA. I'm Farah, and I will be presenting preliminary hazard analysis, which is PHA. PHA is basically the first attempt in categorizing and identifying the hazards that are present in a system or a process. So basically, it lists down things like operating conditions as well as the hazardous components that are present. So first things first, we have studied some of the accidents that have happened to prevent history from repeating itself. So the first one is the tragic accident in Wabash River that happened in April 2008. So basically what happened was that two men operated on one of the openings on the gasifier unit. So there was this weak leakage and they tried to tighten the bolts of the flange opening from approximately 150 feet in air to stop the leakage. And it actually led to explosion because the flange opening came off and it led to 2 casualties. So the next case study is the explosion in the Yuma gasification plant in China, which happened in July 2019. So there is still no known cause of explosion. However, the problematic part about this plant is that it is located near schools, as well as gas station and even residential area. So when the explosion happened, it collapsed the building. Like the buildings within the 500-meter radius collapsed, as well as it negatively affected the residential area, like the houses as well. So what happened was there were 15 casualties and 256 injuries in total. So after studying the previous accidents that have happened, the next step would be material and chemical hazard needs to be identified. So how we did it is basically we've identified all of the chemicals and materials that are present, and we used MSDS material safety data sheet as a reference. Since MSDS documents the chemical safety of all of the chemicals, and so some of the information that are present in the MSCS, we extracted them and tabulated them. And some of the information are toxicity properties, flammability properties, as well as stability and reactivity. So for our case, we have around 14 chemicals or materials that are present in our plant. So to summarize the table, most of the chemicals are fairly harmless at low concentration, and they are pretty much stable at normal conditions as well. So some of the chemicals are like methanol, carbon dioxide, carbon monoxide, and much more. So here are some of the chemicals that are present. And next is the reduction of potential accidents. So basically, hazard is like a form of harm to a person or a particular thing. So when you are exposed to hazard, you are also exposed to risk. You are at risk. So how you can reduce the risk is by identifying all of these hazards, and this simultaneously reduces the potential accidents that might occur. So first things first is a chemical hazard. So for chemical hazard, as you can see, there is a chart, which is some sort of a control measure chart. So at the bottom here, going upward, vertically upward of the pyramid, it increases the effectiveness. So the bottom part, which is wearing PPE, administrative and work practice controls, engineering controls, are all to reduce exposure to the hazards. However, for elimination or substitution, it eliminates the chemical hazard completely. So it does not only reduce the exposure, but it eliminates the chemical hazard. So next will be the pressure and temperature, which are the operating conditions. So the temperature for the gasification is around 800 degrees C. And also some gasification plants can actually go as high as 1200 degrees C. And also for our case, we're also using absorber at around 10 bar, which will be discussed later on. So this is fairly high pressure and very high temperature. So basically every unit, the operating conditions must be identified. This is because we want to ensure that the operators know what they are dealing with. And finally is the plant and site layout. So of course it is normal for every plant to be in the presence of flammable gases and also vapors, and to be operated at high operating conditions. And that is when plant and site layout planning is highly crucial, because, for example, a unit and another unit, there must be a safe distance in between. And that is because we want to prevent domino effect from happening, as well as to reduce the chances of escalation. So not only we can operate the plant in a very safe manner, we can also build the plant in a very profitable manner as well. So finally, there are several safety acts and regulations that we need to abide, since our plant location is in Nibong Tebal, Penang, Malaysia. So these acts are generally to protect the well-being of persons, as well as to control the pollution. So the acts are like Occupational Safety and Health Act 1994, Factories and Machinery Act 1967, and Environmental Quality Act 1974. So that's all for this part. I will pass the floor to Sanjeev. Thank you.
Now I will briefly present about the conceptual design of the project. Prior to the steam gasification process, PP firstly undergoes a pre-treatment process. The assumption here is that the plant operates for 345 days a year with an inlet flow rate of PP at 60,400 kilograms per hour. Feed PP waste first enters the washer, where water is pumped in to remove any impurities present on the surface of the PP. The assumptions made here are water to PP ratio to be 1 to 1. Feed PP contains dust or impurities in form of carbon. Moisture absorption capacity of PP is 0.03 weight%. Next, PP enters the granulator, where it is grinded into smaller sizes before entering the dryer. This is done to increase the conversion efficiency. In the dryer, nitrogen gas is introduced to carry out the drying process. This is because the nitrogen gas provides a moisture-free environment by displacing existing oxygen molecules. Assumptions that are made here are drying temperature to be 110 degrees Celsius and nitrogen gas inlet 60 kilogram per hour. In the last pre-treatment process, PP enters a cyclone before it enters the gasifier. This is done to separate the gas and solid products by rotational and gravity means. The assumptions made here is that cyclone efficiency to be 99.99%. So the entire pre-treatment process is carried out to ensure smooth feeding of PP to reactors in the later on processes for better conversion. Presented here is the entire simulation of conversion of PP into products by using Aspen Plus program. There are several units present such as gasification unit, carbon dioxide absorption unit, methanol synthesis unit, DME unit, and hydrogen separation unit. Shown here is the process flow diagram of our project. I will discuss about the gasification unit, and EZZA will further explain about the remaining processes. Upon completion of the pre-treatment process, PP is moved into a gasifier to be converted into syngas. The type of gasifier that was chosen is the fluidized bed reactor with olivine as the bed material. The operational parameters are at 800 degrees Celsius and 1 bar. The gasifying agent used are air and steam. This is to obtain a better quality of syngas with higher hydrogen to carbon ratio. The carrier gas used is nitrogen gas as it is an inert gas. Products formed from gasification of PP is primarily syngas. Minor products such as methane, carbon dioxide, water, nitrogen gas, heavy oil, char and tar are also present in small quantities. Next, the syngas produced enters a cyclone where dust, impurities, and char are removed. The cyclone efficiency is assumed to be 97%. Rotational effects and gravity are used to remove these impurities. However, some impurities with smaller size particulate not be completely removed. Thus, the syngas enters a scrubber at where the syngas will come in contact with water, which will be supplied into the scrubber. Impurities will attach to the water and the droplets will be collected at the bottom of the scrubber. Clean syngas then enters the CO2 absorption unit, which EZZA will now discuss about. Thank
Second
you.
one is carbon dioxide absorption unit. In this, it consists of absorber and also stripper. For the absorber, it is to remove carbon dioxide from the syngas, where for the operating condition of the absorber is pressure 10 atm and for the temperature is 40 degrees Celsius. The absorber used is monoethanol amine. For this absorber, to ensure the high efficiency of absorber, you need to use 50-50, which is the concentration of amine is 50% and the concentration of water also 50%. So for the product, it will produce a rich amine and also the syngas, where the rich amine will move to the next column, which is the stripper, which the stripper is to strip off carbon dioxide from amine, where the pressure is only 1 atm and for the temperature is 40 degrees Celsius. For the product, it will produce carbon dioxide and also lean amine, where the lean amine will be recycled back to the absorber to be reused for the removal of carbon dioxide from the syngas. The assumption made here is the removal efficiency is 99%. The next one is for methanol synthesis unit. For the methanol synthesis unit, it consists of 3 units, which is the first one is packed bed reactor. The packed bed reactor is to convert syngas from the methanol. As we already separate the carbon dioxide from the syngas from the carbon dioxide absorption unit, the syngas will go to the packed bed reactor for methanol synthesis unit, where the operating condition is at 10 atm with temperature around 200 degrees Celsius. From the literature review, the ratio of the H2CO2 and CO and CO2 is around 2. However, from our simulation, we got 3.94. This is due to the high quantity of hydrogen in the feed. The product produced from the reactor is methanol, water, and also the unreacted gases. Next, the product will be moved to the second unit, which is flash vessel, which is to separate condensable product from non-condensable reactant. The non-condensable reactant is hydrogen, carbon monoxide, and also the carbon dioxide. In here, the assumption have been made is the removal efficiency is only 50%. The the unreacted gases from here will be go to the hydrogen separation unit, and the remaining will move to the next separator, which is distillation column. For the distillation column, it is to separate methanol from the impurities to get our main product, which is methanol. In here, the assumption that have been made is removal efficiency is around 99%. Moving on to our DME synthesis unit, it is also consists of three main unit, which is the first one is fluidized bed reactor. It is to convert carbon dioxide to DME, where the carbon dioxide is from the CO2 absorption unit just now. The operating condition of this reactor is at 10 atm and temperature is around 160 degrees Celsius. Same goes from the literature review, same goes to H2 over CO2 ratio for the fate is around 3. However, from our simulation, we only need 1.5 ratio. This is due to the high purity of carbon dioxide, which is coming from the stripper. From the reactor, the product that we get is methanol, water, and also the unreacted gases. So the product will be moved to the separator to get our main product, which is DME, to separate DME from the impurities. So the assumption here is removal efficiency is around 99%. The other impurities will go to the next separator, which is distillation column. This is to separate methanol from the impurities, where the methanol will be recycled back to our reactor to be used in order to increase our product. And the assumption here is the removal efficiency is also around 99%. And lastly, on our hydrogen separation unit, which is only consists of membrane separator, it is to separate hydrogen from the rest of gas mixture. It is one of our mitigation to reduce waste, as hydrogen, as mentioned earlier, it can be used in many industry. For our membrane separator, the membrane we use is dense metallic membrane, which is made out of palladium. And in here also, we assume that the removal efficiency is around 99%. That's all for process description. Thank you.
I'm Yuan, and I will briefly discuss about the economic evaluations of our project. So the first part under the economic evaluations is the capital expenditure, capex, and capital investment. So we first calculated the project cost of equipment (PCE) by estimations of price of all the equipments from Alibaba.com, and we sum up the price to get the total PCE here. So after that, we calculate the physical plant cost by using the formulas from textbook C0 2005, and we calculate the PPC from PCE and times with the length factor. And then after that, the TFC can be calculated from PPC times with the factors of fluid solids processing. And after that, we calculate the TWC, which is the working capital, by estimations of 50% of the fixed capital costs. And lastly, we sum up the WC and TFC to get a total initial investment. All the calculations here is based on the formulas from C0 2005. Then after that, we calculate the operating cost and annual operating expenditure of facts. So there are two types of operating costs, fixed and variables. So we sum out the fixed operating cost and variable operating costs as summarized in this table here. So we get the total operating cost of this amount, and we can calculate the production cost by dividing the total operating cost with the total production rate of all products per year to get 3.8 ringgit. Then we calculate the annual income by considering all the revenues earned from the methanol, DME, and hydrogens, which is our main products and also side products, and we get this amount. Then finally, we can calculate the economic potentials. So the economic potential one is calculated from the product value minus the raw material cost. Product value, which is the revenue of the products, and also economic potential 2 can be calculated from EP1 minus cost of utilities. And lastly, EP3 is equals to EP2 minus annualized PCE. PCE is the purchase cost of equipment. So we assume 15 years of plant life and we get this amount. So after evaluating the economic aspect of our plant, we can say that our plant is economically feasible because after considering the raw material cost, cost of utilities, and analyzed PCE, we still can earn 474,974,224 ringgit per year. So that's all for the economic evaluations part. Alright, thank you so much, Ranhan. Now I will be addressing the heat integration part of our project. So heat integration is very important in minimizing or reducing the energy or heat in an industry. The thing about typically in industry is that the energy or heat consumption and generation is very excessively high, and that is not favorable economically, and that is because it is costly. So heat integration actually plays a vital role in reducing the thermal energy and also reducing the cost as well. So in this chapter, we use the pinch analysis method. So here are some of the steps. So for the first step is data extraction. So this is a process flow sheet that we obtained from Aspen Plus simulation, and there are heater and coolers here and there. So what we did is we just manually extracted the data from Aspen Plus, and we tabulated them into this. So we found that there are 6 streams in total, 3 hot streams and 3 cold streams. And from Aspen Plus, we got the supply target temperature and also the heat load. And we managed to calculate the CP based on the formula of Q equals to CPDT. And here are the data that will be used for the head design later on. So next will be the determination of the suitable delta T mean. Like for this table, it summarizes the typical delta T mean values for the respective industrial sector. For our case, it falls under the chemical industrial sector, which is the T mean value is around 10 to 20 degrees C, and we chose 20 degrees C. Next will be the PTA cascade, CC, GCC, and minimum utility requirement. So the first one is the problem table algorithm. So basically, here's a pinch temperature. It also mentions the QH mean and QC mean. Same goes to cascade, which talks about the pinch temperature 790 degrees C, as well as the minimum hot utility and minimum cold utility of 609,125.90 kilowatt. So for the pinch temperature, we can actually get the hot and cold pinch temperature by simply adding or subtracting half of the delta T mean. So we got 780 and 800 degrees C. So next will be the minimum utility duty requirement. So of course, HIN gives the minimum and minimum of heating and cooling duties. However, they also provide the minimum number of heat exchangers, which is 7. So next will be the composite curve. The concept is still the same. This range shows the QC mean, and this range shows the QH mean. As for grand composite curve, this is the pocket, and there's also another pocket here. So pocket actually signifies that the within this region, there is sufficient heat exchange. And next will be the heat exchanger network design itself. So here is the streams arrangement. Based on the data that we have put in HIN. So we got the streams arrangement before putting in the heat exchanger. So carrying out hand design, we actually have to follow some of the rules. Like for example, one is the CP rule. So below pinch, the heat capacity of hot stream must be higher than heat capacity of cold stream, and the other way around for above pinch. And another thing is that the coolers can only be present in below pinch area, and only heaters can be present in above pinch area. So although the CP rule should not be violated, however, if away from the stream, away from the pinch, it can actually violate the CP rule. The CP rule does not matter anymore. So for our case, this is the final hand design. There are 7 heat exchangers in total, and that is because we cannot perform loop and path. When we perform loop, the timing violation is present, and the only way to solve the loop issue is that by carrying out path. So by carrying out path, we actually need heater because path literally means the connection of heater to cooler. So timing violation is not feasible. So we just stick to this as the final hand design. So finally, the utility reduction. Previously, before key integration, our utility is as high as 1 million, and we managed to reduce around 700,000 kilowatt of that, which means 54.1% reduction of duty after heat integration. And this proves that heat integration is very effective in reducing thermal energy and reducing costs. So this is how the process flow diagram looks like before heat integration, all the heaters and coolers, and how it looks like after heat integration. Thank you so much. That is all for heat integration, and I'll pass the floor to Yuan. Thank you.
I'm Yuan and I will going to discuss about the process instrumentations and control of our project. So I would like to start with a simple introduction of the P&ID. So P&ID is very important for a chemical process to ensure the consistency and improve the quality of the product by maintaining a certain ratios of feeds and maintain the parameters such as pressure and temperatures, and also to boost the energy efficiency of the process. Besides, the P&ID can reduce the labor cost by substituting the labor with the automated process instrumentations and controls for the plant's operations. Besides, it can also ensure the safety of the plant. For example, with the installations of pressure relief valve, we can prevent the accidents of excessive pressures of the equipment. So there are several variables under the P&ID, which are control variable, manipulator variable, and disturbance. So there are different types of control systems, namely feedback, feed-forward ratio, and cascade controls. And the description, advantages, and disadvantages of all these control systems are listed as follows. So this is the P&ID diagram designs for our chemical plant. So without further ado, I would like to start with the discussions for the process control for major equipments in our process. So first, the gasifier. Under the gasifier, there are 3 control objectives. So first is to maintain the ratio of gasified agent feed into the reactor by manipulating the air flow rate and also steam flow rate by the ratio control type. So next, we can maintain the pressure inside the reactor by manipulating the flow rate of the gas products here. And lastly, to maintain the temperature inside the reactor, we can adjust the flow rate of gasifying agent feed here. Next, carbon dioxide capturing unit is represented by V2 and V3 here. So V2 is the adsorber and V3 is the striper. So the first control objective is to maintain the pressure of the adsorber and striper by manipulating the flow rate of the product's gas stream here and also the striper here. So then we can maintain the level of the liquid level of the adsorber and striper by manipulating the flow rate of exiting liquid stream by the feedback control here and here. And lastly, we can maintain the inlet feed flow rate by adjusting the flow rate of syngas here and also adjust the flow rate of the lean amide inlet here. Next, methanol synthesis reactor R2. There are also 3 control objectives. So to maintain the pressure reactor similar as before, we adjust the flow rate of the product stream. And to maintain the temperature inside the reactor, we adjust the flow rate of steam to heat up the reactor. And lastly, to maintain the inlet feed flow rate, we adjust the flow rate of the feed represented here by the feed-forward control. And then proceed to the DME, the synthesis reactor R3. Similarly, to maintain the liquid level of reactor, we manipulate the flow rate of liquid product here. And then to maintain the temperature inside the reactor, we manipulate the flow rate of the steam to heat up the reactor. And lastly, to maintain the inlet gas feed flow rate, we adjust the feed of the gas feed by using the feed forward control. Moving on to the membrane separator V8. To maintain the pressure inside the reactor, we also adjust the flow rate of the gas product here. And to maintain the liquid level of separator, similarly, we adjust the flow rate of liquid outlet here. And then, similar as before also, to maintain the inlet feed flow rate, we adjust the feed flow rate of feed here by the feed forward control. So moving on to the distillations column, there are 3 distillation columns in our process. So there are 4 control objectives for the distillation column. First, to maintain the pressure inside the column, we use a common way of maintaining the pressure inside the column by manipulating the flow rate of cooling water to condense the overhead reflux here. Then we maintain the temperature inside the reactor by controlling and manipulating the flow rate of overhead reflux distillate. And then to maintain the liquid level of the distillation column, we adjust the bottom flow rate. And lastly, to maintain the inlet feed flow rate, similarly, we adjust the flow rate of feed stream by feed forward control. So next, we proceed to the process control for minor equipment. So separator V1, which is a scrubber in the gasification unit, we maintain the pressure of the separator by manipulating the flow rate of exiting gas here. And then to maintain the liquid level of the separator, we adjust the flow rate of exiting liquid mixtures represented by the stream number 8. And also to maintain the inlet feed flow rate, we use feed forward control to control the feed flow rate of the feed stream. Then for the flash vessel V4 in the methanol unit, we maintain the pressure inside the vessel by manipulating the flow rate of exiting gas. And then to maintain the liquid level in the reactor, we adjust the flow rate of exiting liquid similarly. And to maintain the inlet feed flow rate, we adjust the feed flow rate of the feed stream by feed forward control. And lastly, for the heat exchanger and coolers, as this in our process, we have to maintain the temperature and temperature outlet stream of the outlet stream temperature of from the heat exchanger and cooler, and by doing so, we manipulating the flow rate of the hot stream and cold stream represented by these diagrams using the feedback control. So that's all for the process instrumentations and control part.
Hi, my name is KUOL. I'm going to discuss about safety and loss prevention. It will cover hazard and operability study and the plan layout. So, hazard and operability study is defined as a technique used to determine all possible hazards that may arise in the plan. It identifies the deviation from the design intent, causes and consequences, and proposes the solutions. In hazard and operability studies, there are many terminologies that are used. These terminologies are defined as below. 1 is node, which refers to location at the process parameters. 2 is parameter, which refer to variable associated with the process condition. 3 is intention, which refer to the expected operation of the plan in absence of deviation at the study nodes. 4th is deviation, which refer to changes from the desired intent. 5th is cause, which refer to reason for the deviation. 6th is consequent, which refer to effects of the deviation. 7th is safeguard, which refer to action taken to alleviate the consequences. 8th is guide word, which refer to word used to quantify or qualify the intention in order to guide and stimulate the brainstorming process to discover the deviations. Example of guide words include less, more, none, reverse, among others. This table here is the hazard study for the node R1 or gasification reactor unit, where the waste plastic is converted to syngas. The parameter study here is the flow using 3 guide words no, less, and more. So no flow deviation can be caused by control valve failure. It can also be caused by pipe blockage. The consequences of no flow deviation would be no production of syngas and the rupture of the pipe. The safeguard taken to alleviate the consequence of no flow include performing regular check on the control valve and piping condition, installation of the flow alarm. Second deviation is less flow. Less flow deviation can be caused by partial closure of the valve. It can also be caused by partial blockage of the pipe. The consequences of less flow would be low syngas production and low waste plastic conversion to syngas. The safeguard include addition of low flow alarm and performing regular check on the valve and the piping condition. Lastly is the more flow deviation, which can be caused by malfunction of the valve and also increase in pressure of the feed line. The consequence of more flow can be decreased rate of conversion. The safeguards taken include installation of the flow regulator. Furthermore, I will discuss about the plant layout. Plant layout refers to designation of space and arrangement of major equipment to reduce the cost in the plant. It is divided into three areas, which include the non-process area, the low hazard process area, and the high hazard process area. The plant layout helps in achieving safety and preventing loss by limiting exposure to hazard, ensuring safe and efficient maintenance, and also containing accident to specific areas. The non-process area in this figure would include the recreational park, multi-purpose hall, the car parking area, administrative office, prayer room, and cafe. They are located far away from the process areas to reduce the consequences of accident that might occur. Next is the low hazard process area. This area is the area with chances of accident happening. The low hazard process area in this figure include the effluent and water treatment unit, the control room, the utilities, maintenance and facilities workshop, and the shipping zone, which is this in the red area. Lastly, but not least, is the high hazard process area. This area is where the processing of chemical takes place at extreme pressures and temperature. They include the gasification reactor unit, the DME synthesis reactor unit, methanol reactor synthesis unit, the two distillation column, and hydrogen separator. They are located in the middle of the plant to avoid obstructing during the evacuation in case of an emergency. Also, the safety control tools are put in place in the plant to minimize the consequences of accident on the personnel and the machineries. For conclusion, many factors such as feasibility of project, location, infrastructure are assessed during plant design. In our case, Nibong Tibal in Pulau Pinang was chosen for building the plant because of its strategic location, access to market, and good transport facilities, among other factors. Also, during the plant design, many parameters were considered when choosing the types of process, mode of operation, reaction, and gasifying agent to ensure production of high-quality syngas. Besides that, the process design was environment-friendly, low cost, and consumption of less energy. The simulation was performed using Husband Plus software where high yields and pure products were obtained. The yield is greater than 65% and purity is greater than 99%. The process optimization and heat integration were conducted to increase production, and the cost and energy consumption were also minimized, hence the heat recovery is 51%. HAZOP for major and minor equipment was also conducted to ensure the safety of machineries and workers. Lastly, but not least, the economic analysis was performed and the project was found profitable with an amount of 474,974,224 ringgit per year from sales of product. That's all from us. Thank you for listening.